Welcome to the Deep Dive. I'm really glad you're with us today. We're going to be unlocking the secrets of something that is, well, it's quite literally everywhere. Just think about milk turning into curd, maybe, or the signals firing in your brain right now.
Or even the device you're listening on.
Exactly. The common thread running through all of it, it's chemistry. It's this fundamental science that looks into, well, everything that has mass and takes up space.
And, at its core, science, as our sources really stress, is this ongoing human effort. It's about trying to systematize knowledge, right? To describe and understand nature.
Right.
And chemistry specifically is that branch, focusing on the preparation, properties, structure, and reactions of material substances. It's definitely more than just, beakers and formulas.
That's a perfect way to put it. And it sets up our mission for today really well. We've gathered a stack of sources, articles, notes, research, and our goal is to pull out the really key nuggets for you, give you a shortcut to being genuinely well-informed. In this deep dive, it isn't just about listing facts. It's about understanding the journey, this incredible human journey of discovery in chemistry, and really grasping its huge impact on, well, everything in our lives.
So our specific focus today is the really basic foundational concepts. We want to unpack what chemistry actually is. We'll trace how our understanding developed, from ancient times right up to modern science. We'll look at why it's so crucial and explain the basic ways we measure and quantify the material world.
So by the end of this, you should have this powerful kind of underlying framework for understanding basically everything around you, from the tiniest atom to, the biggest natural processes.
So, yeah, let's get into it.
Okay.
When we first think about chemistry, maybe we picture bubbling flasks, maybe complex equations on a blackboard.
Sure, the classic image. Right. But underneath all that, like our sources articulate so well, it's really this ongoing human effort to systematize knowledge, to describe and understand nature. It's basically the study of how stuff is made, what it's like, how it's put together, and crucially, how it changes.
And there's a wonderful quote from the chemist Roald Hoffmann that captures this. He said, "Chemistry is the science not so much of the 100 elements, but of the infinite variety of molecules that may be built from them."
Infinite variety.
I love that. It really sets a tone of wonder, doesn't it? It shows how this relatively small set of basic building blocks can create just an almost endless array of different things.
It really does. It highlights that creative potential, like you said.
Yeah.
We often think of chemistry in modern labs, right? But its roots, they go way back. They're ancient and honestly kind of surprising.
Oh, absolutely. And it's here we find some just remarkable human ingenuity. Modern chemistry, the way we understand it now, it didn't just pop up out of nowhere seeking pure knowledge. Its early development was actually pushed along by these two, well, almost mythical goals, really ambitious stuff.
Which were?
The search for the philosopher's stone, this legendary substance thought to turn base metals like lead into gold.
Right, the ultimate alchemy goal.
And the other was the quest for the elixir of life, believed to grant immortality.
So turning lead into gold and living forever. Yeah, talk about high stakes.
Exactly. And these huge ambitions, they really spurred on practices like alchemy. That's sort of an early, maybe more mystical form of chemistry focused on transformation, and also iatrochemistry, which was chemistry applied to medicine. This was mainly between about 1300 and 1600 CE.
And then modern chemistry started to emerge later.
Yeah, it really began taking shape in 18th century Europe. And it was heavily influenced, it's important to note, by Arab alchemical traditions, which had really flourished centuries before.
Okay, but here's something that really jumped out at me from the sources, this aha moment. Long before modern European chemistry, ancient India had developed this, well, remarkably sophisticated understanding of chemical processes.
Yes, absolutely. This indigenous knowledge, it was known as Rasayan Shastra, basically the science of chemistry.
Rasayan Shastra. Okay, so what kind of chemical know-how do they actually have?
Well, just the archaeology alone is pretty compelling. You look at discoveries from sites like Mohenjo-Daro and Harappa,
Okay.
and you see widespread use of baked bricks. That points to mass production of pottery, which is really one of humanity's earliest chemical processes, right? It involves precise mixing, shaping, heating.
Sure, controlling fire, material.
Exactly. And they used gypsum cement in construction. They even produced something called faience. It's an early type of glazed ceramic used for ornaments. That suggests a really advanced grasp of material science back then.
So ceramics construction. What about metals? That seems key.
Oh, definitely. They had well-established indigenous technologies for extracting and working with copper and iron. The Harappans, for instance, they melted and forged things from lead, silver, gold, copper.
Wow.
And crucially, they even knew how to make copper harder, better for tools and artifacts by alloying it, mixing it with tin and arsenic. That shows a really deep understanding of material properties. We also find glass objects colored with metal oxides dating back thousands of years.
That level of metallurgy is, really impressive for the time. Were there other chemical processes they understood that maybe mirror later discoveries?
Oh, many. The Rig Veda, which dates from around 1000 to 400 BCE, actually describes tanning leather and dyeing cotton.
Really?
Yeah. And our sources mention this distinctive golden gloss of the black polished ware of northern India. Apparently, it was a chemical mystery later on because the technique, likely involving precise kiln control, couldn't be replicated.
A lost art, basically.
Seems like it. And then you have ancient texts like the Charaka Samhita. It reveals knowledge of preparing various acids, sulfuric acid, nitric acid, oxides of copper, tin, zinc, sulfates of metals, carbonates too. They even understood fermentation processes for making medicinal liquors called asavas.
So we're talking early pharmaceutical chemistry, industrial type processes.
Mm-hmm.
And I think I read something about things that go bang.
You did. Texts like the Retapanashada and also ancient Tamil writings, they describe preparing gunpowder and even fireworks.
No way.
Yeah, using sulfur, charcoal, saltpeter, that's potassium nitrate, mercury, camphor. It really speaks to an advanced understanding of chemical synthesis and, releasing energy chemically.
That is remarkable. Were there, famous figures associated with these breakthroughs, like the Lavoisier or Dalton of ancient India?
Well, Nagarjuna, around 800 CE, is a really significant figure, a great Indian scientist, chemist, alchemist, metallurgist. His work, the Rasratnakar, talks about mercury compounds and methods for extracting metals like gold, silver, tin, copper. There's another text from about the same time, Rasamam, which describes different kinds of furnaces, ovens, crucibles. It even explains how to identify metals by the color of their flame when heated.
Flame tests. We still use that in basic chemistry labs today.
Exactly. It's a form of analytical chemistry right there.
Amazing. What about something more, maybe, everyday? A common household item?
Well, how about soap? The credit for inventing soap is often given to Chakrapani. He also discovered mercury sulfide. He used mustard oil and specific alkalis to make it, and the evidence suggests Indians were making soaps as early as the 8th century CE.
Soap. Wow. That's a fundamental invention for hygiene in daily life.
Absolutely. A practical application of chemical knowledge that definitely improved life.
And it seems it wasn't just practical stuff. I'm thinking about, ancient art that still looks incredible today.
Yes. The paintings at Ajanta and Ellora, they're still so vibrant after centuries. It's really a testament to their advanced understanding of pigments and binders, the stuff that makes paint stick and last. Varmi here's Brihat Samhita from the 6th century CE describes making this glutinous wall material, like a plaster, from plant extracts and resins. And they were pioneers in perfumes, cosmetics, even hair dyes, all derived from natural sources.
Incredible.
And even paper was known in India by the 17th century, and ink from way back in the 4th century.
This historical depth is just, mind-blowing. But maybe the most, astounding contribution for me, looking back from today, is something really fundamental about matter itself.
You must mean the concept of the paramanu.
Yes. Tell us about that.
Okay, so this idea originated with Acharya Khanda, who is also known as Kashyap, around 600 BCE. He formulated this theory of paramanu, these very small, indivisible particles. He described them as eternal, indestructible, spherical, too small to see, and interestingly, in constant motion.
Wait, 600 BCE. Hold on. That's like 2,500 years before John Dalton proposed his atomic theory in Europe.
Exactly. It's an absolutely incredible conceptual leap for that time.
That's astonishing.
Khanda even suggested that different types of atoms existed, corresponding to different classes of substances, and that they could combine in pairs or triplets, interacting through sort of unseen forces.
Wow.
And what's more, the Charaka Samhita, that metal text we mentioned, discusses reducing the particle size of metals to make medicines, known as bhasmas. Modern analysis shows these actually contain nanoparticles.
Nanoparticles. So an intuitive grasp of what we now call nanotechnology thousands of years ago.
It certainly seems that way, a truly remarkable insight into manipulating matter at a very fine scale.
So much advanced knowledge back then. What happened? Why did these indigenous techniques seem to fade?
Well, it's complex, but unfortunately, with the rise of Western medicine and then the later arrival of modern European-style scientific methods in India, particularly in the late 19th century, many of these sophisticated traditional techniques started to decline. It took time for Indian scientists to fully adapt and integrate these newer approaches, and during that period, foreign products and methods often became more dominant.
It's a really powerful reminder, isn't it, that knowledge develops in different ways across the globe, and there's so much we can learn from looking at these diverse historical paths.
Yeah, absolutely.
Okay, so let's bring it forward. How does all this rich history connect to chemistry's impact on our world today?
Well, chemistry's role today is just completely central. It's woven into pretty much all the other sciences, physics, biology, geology, material science.
Right.
Its principles are working away in every aspect of our daily lives, often completely unseen, you know?
Yeah, you're right. We're talking about everything from understanding how our brains actually work, the signals
Complex biochemistry, yeah.
to predicting weather patterns, even how our computers operate. And then there's the huge industrial side producing basically everything we use. Fertilizers, plastics, medicines, paints, metals.
The list is endless, truly. And chemistry has been absolutely instrumental in dramatically improving our quality of life. Think about healthcare. Chemistry gives us the tools to isolate compounds from nature or synthesize life-saving drugs in the lab. You know, drugs like cisplatin and Taxol for cancer therapy or AZT for AIDS patients. Huge impact.
Huge. And it's not just medicine, right? It feels like chemists are creating entirely new materials now that seem almost like science fiction.
It can feel that way. Chemists design and synthesize materials with very specific tailored properties, magnetic, electric, optical properties.
Like what?
Things like superconducting ceramics or conducting polymers, plastics that conduct electricity, or optical fibers that carry our internet data. These are technologies that were just, well, unimaginable not that long ago.
And it's not only about creating new things, is it? It's also fundamental to tackling problems we already face, especially environmental ones.
Yes, that's a critical area. Chemistry plays a huge role there too. For example, developing safer alternatives to chemicals that harm the environment.
Like the ozone layer issue.
Exactly. Chemists successfully synthesized safer alternatives to CFCs, those refrigerants that were depleting the ozone layer. That was a major success story. Yeah.
But we also have to acknowledge there are still massive environmental challenges. Managing greenhouse gases, for instance, is an urgent ongoing concern for chemists worldwide.
Which really means the future needs more chemists, right? More bright minds tackling these big issues.
Absolutely. Understanding complex biochemical processes, figuring out how to use enzymes on a large scale for green chemistry, synthesizing new materials with exotic properties. These are the kinds of challenges that need talented chemists. And underpinning all of that, all these applications and challenges, is the basic understanding of the stuff everything is made of. Matter.
Matter. Yeah, simple definition. Anything that has mass and occupies space. You, me, the air, this microphone, it's all matter.
Right.
And we usually talk about the three main physical states.
Yeah.
Solid, liquid, gas. But what's really cool is how the behavior of the particles within them explains their properties.
You mean how they're arranged and how they move?
Precisely. In solids, the particles are packed tightly, usually in an orderly way. They can vibrate, but they can't really move around much. That's why solids have a definite volume and a definite shape.
Okay.
In liquids, the particles are still close together, but they can slide past one another. So liquids have a definite volume, but they take the shape of their container.
Makes sense.
And then in gases, the particles are far apart, moving randomly and quickly. They just spread out to fill whatever container they're in. So gases have no definite volume and no definite shape.
And crucially, these states aren't permanent.
Not at all. They can change from one to another just by changing the temperature or pressure. You heat ice, it melts to water. You heat water, it boils to steam.
Yeah.
That interconvertibility is fundamental.
Yeah, underlies everything from making tea to industrial processes. Okay, so we have matter in different states. How do chemists actually categorize the types of matter?
Right. So at the big picture level, we can classify matter as either a pure substance or a mixture.
Okay, pure substance first.
A pure substance has a fixed composition. All its constituent particles, atoms, or molecules are chemically identical. Think of pure gold or pure water, HO.
And pure substances themselves can be broken down further.
They can, into elements and compounds. An element consists of only one type of atom. Could be individual atoms like sodium, Na, or molecules made of only one type of atom like hydrogen gas.
Got it.
Yeah.
One type of atom only.
Yep. A compound, on the other hand, is formed when atoms of two or more different elements combine chemically in a fixed ratio.
Fixed ratio, that sounds key.
It is. And here's the really interesting part. The properties of a compound are often completely different from the properties of the elements that make it up.
Can you give us a really clear example of that?
Sure. The classic one is water, HO. It's made of hydrogen and oxygen. Now, hydrogen gas is highly flammable.
Right.
And oxygen gas actively supports combustion and makes fires burn better.
Definitely.
But when they combine chemically in that fixed 2-to-1 ratio, they form liquid water, which we use to put out fires.
Huh. Yeah, that's a dramatic difference. Total change in properties.
Exactly. That transformation is the hallmark of forming a compound.
Okay, so that's pure substances, elements and compounds. What's the other main category?
Mixtures. A mixture contains two or more pure substances, but they aren't chemically bonded, and they can be present in variable ratios.
Variable ratios, okay.
Think of the air we breathe. It's a mixture of nitrogen gas, oxygen gas, argon, Caroo, and other trace gases. The proportions can vary slightly. Or, sugar dissolved in water, you can make it more or less sweet.
And unlike compounds, you can usually separate mixtures using physical methods.
Generally, yes. Things like filtering, evaporation, distillation, or even just picking things apart by hand sometimes. The components retain their individual identities in a mixture.
And mixtures themselves have different types too, right?
They do. We talk about homogeneous mixtures and heterogeneous mixtures.
Modular.
That means the composition is uniform throughout. The components are perfectly mixed down to the molecular level. You can't see the different parts. Salt water is a good example, or air, or alloys like brass.
Okay, completely uniform. So heterogeneous must be
Non-uniform composition. You can often see the different components. Think of sand mixed with iron filings, or rocks and soil, or even pulses with some stones mixed in. The composition varies from one part of the mixture to another.
Got it. Pure substances versus mixtures. Homogeneous versus heterogeneous. That gives us a good map of matter. But to really do chemistry, it all comes down to measurement, doesn't it? Quantifying things.
Absolutely essential. Every substance has unique characteristics, properties that chemists measure. These properties help us describe it, identify it, understand how it behaves, and we broadly group these into two types.
For sure.
First, physical properties. These are characteristics you can measure or observe without changing the substance's chemical identity. Things like its color, its odor, its melting point, boiling point, density, hardness. You can measure the density of water without turning it into something else.
Okay, makes sense. And the other type?
Chemical properties. These describe how a substance reacts or changes to form different substances. To observe these, a chemical change has to happen.
So things like
flammability, does it burn in oxygen? Acidity or basicity, how does it react with acids or bases? Its reactivity with other specific chemicals, like does it corrode in air? These are all chemical properties.
And to study any of these, physical or chemical, we need numbers.
Yeah.
And numbers need units.
Precisely. A measurement without a unit is meaningless in science. If I say the length of this room is 6, you'd ask 6 what?
Feet, meters, miles.
Exactly. So every quantitative observation needs a number and a unit. Historically, there were different systems: the English system, feet, pounds; the metric system, meters, grams, which caused a lot of confusion.
Right, especially in international science.
Which led to the need for a common global standard. And that standard is the International System of Units, usually just called SI. It was established in 1960.
Okay, SI units. What are the basics?
SI defines 7 base units for fundamental scientific quantities. There's the meter, M, for length, the kilogram, kg, for mass, the second S for time, the ampere, A, for electric current, the Kelvin, K, for thermodynamic temperature, the mole for amount of substance.
Until they come back to the mole.
Oh, yes.
Yeah.
And the candela CD for luminous intensity. Most other units we use, like volume, cubic meters, or speed, meters per second, or density, kilograms per cubic meter, are derived units built from these base units.
Now, here's something I find really fascinating. How are these base units actually defined? Is there still, like, a master kilogram bar somewhere?
That's a great question because it changed recently. Historically, yes, the kilogram was defined by a specific platinum iridium cylinder kept near Paris.
Right, I remember reading about that.
But what's truly amazing about modern SI is that the definitions are increasingly tied to fundamental constants of nature, things that are believed to be universal and unchanging.
So not tied to a physical object anymore.
Not for the kilogram since 2019. The meter, for example, is defined based on the fixed numerical value of the speed of light in a vacuum. And the kilogram is now defined in terms of the Planck constant, a fundamental constant in quantum mechanics.
Wow.
This makes the definitions incredibly precise and, importantly, reproducible anywhere in the universe, in principle. National labs like the National Physical Laboratory, NPL, in India work constantly with international bodies to maintain and refine these standards. It really underpins all of modern measurement science.
Tying our basic units to the fundamental constants of the universe. That's a profound shift. And for dealing with really huge or tiny numbers in SI, we use prefixes, right?
Absolutely. Prefixes make life much easier. Kilo means 1,000 times, like kilogram. Milli means 1,000th millimeter. Micro, a millionth. Nano, a billionth. Pico, a trillionth. It avoids writing endless zeros.
Very useful in chemistry, I imagine. Okay, let's quickly touch on a few specific quantities we measure all the time. Mass versus weight, people often mix those up.
Yes, it's a really important distinction in science. Mass is the actual amount of matter in an object. It's an intrinsic property and it's constant, doesn't matter where you are.
Okay.
Weight, on the other hand, is the force of gravity acting on that mass. So weight depends on the local gravitational field. Your mass is the same on the Earth and the Moon, but you'd weigh much less on the Moon because its gravity is weaker.
Right, so in the lab, we're almost always measuring mass.
Exactly. Using an analytical balance, which compares an unknown mass to known masses, effectively canceling out gravity's effect.
Okay, and volume.
Volume is just the amount of space something occupies. The SI unit is the cubic meter, but in labs, we often use liters or milliliters, m, where 1 LL is the same as 1 cubic centimeter, cml. We use tools like graduated cylinders, burettes, pipettes, volumetric flasks for measuring liquid volumes accurately.
Got it. And density.
Density is simply mass divided by volume, mass per unit volume. Its SI unit is kilograms per cubic meter. But grams per cubic centimeter, GCML, or grams per milliliter, GML, are very common in chemistry labs. Density tells us how tightly packed the matter is.
Why things float or sink, basically.
Fundamentally, yes. It governs buoyancy.
And temperature, we have a few different scales for that.
We do. The most common are Celsius, degrees C, Fahrenheit, degrees F, still used in some places like the US and the SI unit, Kelvin K.
And Kelvin is special, right?
Yeah, the Kelvin scale is an absolute temperature scale. It starts at absolute zero, 0K, the theoretical point where all particle motion ceases. This means Kelvin temperatures are always positive. There are no negative values, unlike Celsius or Fahrenheit. That makes it very convenient for many scientific calculations.
Okay. Now, a crucial point.
Yeah.
No measurement is ever perfectly exact, right? There's always some uncertainty.
Yeah.
How do chemists deal with that?
That's a fundamental reality of experimental science. Every measurement has some degree of uncertainty. It comes from the limitations of the instrument itself and also the skill of the person doing the measurement.
So how do we handle the numbers, especially when they're incredibly big or small, like the number of atoms in something?
Right. For those really huge or tiny numbers like Avogadro's number, which is enormous, or the mass of a single hydrogen atom, which is minuscule, we use scientific notation, it's a way of writing numbers as a coefficient multiplied by 10 raised to a power, like 6.022 by 10 times with the meter. It makes these unwieldy numbers manageable and clear.
Okay, scientific notation for scale. And what about indicating how reliable a measurement is?
That's where significant figures, or sig figs, come in. Significant figures in a measured number include all the digits that are known with certainty, plus one final digit that is estimated or uncertain.
So they tell you the precision of the measurement.
Exactly. They're crucial because when you do calculations with measured numbers, the result can't be more precise than your least precise measurement. There are specific rules for determining sig figs and for rounding off calculations correctly to reflect the actual precision.
Right, and closely related is the difference between precision and accuracy.
Yes. Very important distinction. Accuracy refers to how close a measurement is to the true or accepted value. Precision refers to how close multiple measurements of the same thing are to each other.
Can you give an example?
Sure. Imagine 3 students weighing a sample that truly weighs 2.00 grams. Student A gets 1.95 grams, 1.93 grams, 1.94 grams. These are precise, close to each other, but not accurate, far from 2.00 grams.
Okay, consistently wrong.
Right. Student B gets 1.99 grams, 2.05 grams, 1.96 grams. These are less precise, more spread out, and also not particularly accurate on average.
All over the place.
Yeah. Student C gets 2.01 grams, 1.99 grams, 2.00 gram. These measurements are both precise, close together, and accurate, centered around the true value. That's the goal.
Precise and accurate. Got it. And finally, for calculations involving units.
We use a powerful technique called dimensional analysis, sometimes called the unit factor method. It's a systematic way to convert units by multiplying by conversion factors, which are essentially ratios equal to 1. It helps ensure your calculations are set up correctly because the units must cancel out properly to give the desired final unit. It's a lifesaver for complex problems.
Right. Making sure the units work out guides you to the right answer. Okay, so we've got chemistry, its history, its impact, matter, measurement. Now, how do the elements actually combine? It's not random, is it? There are rules.
Not random at all. They combine in very predictable ways, governed by several fundamental laws, often called the laws of chemical combination. These were figured out mostly in the late 18th and early 19th centuries through careful experiments.
Okay, what's the first big one?
The law of conservation of mass, championed by Antoine Lavoisier around 1789. Based on meticulous weighing before and after reactions, he established that matter is neither created nor destroyed during any physical or chemical change.
So the total mass stays the same. Atoms just get rearranged.
Exactly. The total mass of the reactants you start with must equal the total mass of the products you end up with. Foundational stuff.
Okay, what's next?
The law of definite proportions, sometimes called the law of constant composition, proposed by Joseph Proust around 1799. This law states that a given chemical compound always contains exactly the same proportion of elements by mass, no matter where it came from or how it was made.
So pure water is always 88.8% oxygen and 11.2% hydrogen by mass, whether it's from rain, a river, or made in a lab.
Precisely. Proust showed this with copper, carbonate. Natural samples had the same composition as synthetic ones. A compound's identity is locked to its fixed mass ratio of elements.
That makes sense. A compound is its composition. But what happens if two elements can form more than one compound together? Like carbon and oxygen can make CO and CoO.
Good question. That's covered by the law of multiple proportions, formulated by John Dalton around 1803.
Okay, what does that say?
It states that if two elements, say A and B, combine to form more than one compound, then the different masses of element B that combine with a fixed mass of element A are in a ratio of small whole numbers.
Okay, unpack that with an example maybe.
Sure, let's use your carbon monoxide, CO, and carbon dioxide, CO example. In CO, 12 grams of carbon combine with 16 grams of oxygen. In CRO, 12 grams of carbon combine with 32 grams of oxygen.
Okay, fixed mass of carbon, 12G in both.
Right. Now look at the masses of oxygen that combine with that fixed carbon mass. 16 grams in CO and 32 grams in CO. What's the ratio of 16 to 32?
It's 1 to 2, a small whole number ratio.
Exactly. That simple small whole number ratio, 1.2, between the oxygen masses is what the law of multiple proportions describes. You see similar simple ratios with oxides of nitrogen, compounds of hydrogen and oxygen, water, HEO versus hydrogen peroxide, HO, etc.
Got it. That's elegant. Now, what about reactions involving gases? Is there a special law for them?
Yes, there is. Gay-Lussac's law of gaseous volumes from 1808. Joseph Gay-Lussac observed that when gases react or are produced in a chemical reaction, they do so in volumes that bear a simple whole number ratio to one another, provided all the volumes are measured at the same temperature and pressure.
So volumes react in simple ratios too, just like masses in the previous law.
For gases, yes. For example, he found that 2 volumes of hydrogen gas react with 1 volume of oxygen gas to form 2 volumes of water vapor, steam. The ratio of volumes is 2.1.2. Simple whole numbers.
That seems very neat for gases. Okay, one more law.
One more key one. Avogadro's law, proposed by Amerigo Avogadro in 1811, this was a brilliant insight. It states that equal volumes of all gases at the same temperature and pressure contain the same number of molecules.
The same number of molecules. That's huge. So a liter of hydrogen and a liter of oxygen under the same conditions have the same number of particles.
Yes. And crucially, Avogadro made the distinction between atoms and molecules. He suggested that elements like hydrogen and oxygen might exist as diatomic molecules, not just single atoms, which helped explain Gay-Lussac's volume ratios.
That sounds incredibly insightful, explaining Gay-Lussac's law. Was it immediately accepted?
Actually, no, which is fascinating. Avogadro's hypothesis, despite its correctness and explanatory power, wasn't widely accepted by the scientific community for decades.
Really? Why not?
There was confusion about atoms versus molecules, and Dalton himself didn't initially accept it. It wasn't until about 50 years later, at a major chemistry conference in 1860, that another chemist, Stanislaw Cannizzaro, presented a compelling argument based on Avogadro's work that finally convinced the community.
Wow, 50 years. Science takes time. So these laws, conservation of mass, definite proportions, multiple proportions, gaseous volumes, Avogadro's law, they all set the stage for a comprehensive theory of matter.
Exactly. They provided the experimental foundation for Dalton's atomic theory.
Right. John Dalton again, 1808. He tied it all together.
Yes. He published his ideas in a new system of chemical philosophy. While the idea of atoms goes way back to ancient Greece with Democritus, atomio, meaning indivisible, Dalton's contribution was to make it a proper scientific theory based on the quantitative laws we just discussed.
So what were the main points, the postulates of Dalton's theory?
He proposed, basically, 1, all matter is made of tiny, indivisible particles called atoms.
Yep.
2, atoms of a given element are identical in mass and properties. Atoms of different elements are different.
Makes sense.
3, compounds are formed when atoms of different elements combine in fixed, simple, whole number ratios. That explains definite and multiple proportions.
Right.
And 4, chemical reactions involve only the rearrangement, separation, or combination of atoms. Atoms are not created, destroyed, or changed into atoms of other elements during a reaction. That explains conservation of mass.
That framework really explained those laws beautifully, didn't it?
It absolutely did. It provided the first truly useful microscopic explanation for macroscopic chemical observations.
But it wasn't perfect, right? You mentioned limitations earlier.
Correct. While a huge leap forward, Dalton's theory couldn't easily explain Gay-Lussac's law of gaseous volumes initially until Avogadro's molecule concept was accepted. And fundamentally, it couldn't explain why atoms combine in the specific ratios they do, or what holds them together. That required understanding atomic structure, which came much later with discoveries about electrons and nuclei.
Okay, so Dalton gave us the atomic framework. Now, how do we actually count these incredibly tiny atoms and molecules when we're doing chemistry in the lab? We can't see them individually.
Right. That's where we need ways to relate the macroscopic amounts we can measure, like mass, to the microscopic world of atoms and molecules. This starts with atomic and molecular masses.
Okay, how do we define those?
The modern system is based on a standard, the carbon-12 isotope. Its mass is defined as exactly 12 atomic mass units, a mu, or often just U. The masses of all other atoms are determined relative to this standard.
So an atom with mass 1U is 112th the mass of a carbon-12 atom.
Precisely. Now, most elements exist naturally as a mixture of isotopes atoms with the same number of protons but different numbers of neutrons, so different masses.
Like carbon-12, carbon-13, carbon-14.
Exactly. So the atomic mass listed on the periodic table is actually the average atomic mass. It's a weighted average calculated based on the masses of the naturally occurring isotopes and their relative abundances. That's why carbon's atomic mass isn't exactly 12, it's about 12.011.
Okay. So that average accounts for the natural mix and for molecules.
The molecular mass is simply the sum of the average atomic masses of all the atoms present in the molecule's formula. So for water, you add the average atomic mass of oxygen to twice the average atomic mass of hydrogen.
And what about compounds like salt, NaCl, which don't form discrete molecules?
Good point. For ionic compounds like sodium chloride, which form crystal lattices rather than individual molecules, we use the term formula mass. It's calculated the same way some of the atomic masses in the empirical formula unit, for e.g. 1 Na and 1 Cl.
Okay, so we have relative masses. But atoms are still unbelievably tiny. How do we connect these atomic mass units to the grams we can actually weigh out?
This is the bridge. This is where the mole concept comes in. It's one of the most important concepts in chemistry.
The mole. Okay, break it down for us.
Because we deal with such enormous numbers of atoms and molecules, chemists needed a convenient unit for the amount of substance, analogous to how we use a dozen for 12 things, or maybe a gross for 144.
So the mole is like a chemist's dozen, but much, much bigger.
Much, much, much bigger. The mole, symbol .mol, is the SI base unit for the amount of substance. 1 mole is defined as containing exactly 6.0221400076 times 10^7 elementary entities. Atoms, molecules, ions, whatever particle you're counting.
That number, 6.022 times 10 to the 23rd. That's Avogadro's number, right?
Yes, that's Avogadro's constant. N0 by 820 by 820 by 90. It's a staggering number. 602 sextillion. It's hard to even comprehend how huge it is. More atoms in a mole of carbon than grains of sand on all Earth's beaches, by far.
Wow. So 1 mole of anything carbon atoms, water molecules, sodium ions contains that specific enormous number of particles.
That's the power of it, yes. And here's the crucial link to mass. The mass of 1 mole of any substance, expressed in grams, is numerically equal to its atomic mass, molecular mass, or formula mass expressed in atomic mass units.
Wait, say that again.
The mass of 1 mole of a substance in grams, which we call its molar mass, has the same numerical value as its formula mass in U.
Okay, so carbon's average atomic mass is about 12.014 U. That means 1 mole of carbon atoms weighs 12.01 unfined grams.
Exactly. And water's molecular mass is about 18.015 U, so 1 mole of water molecules weighs 18.015 grams. This gives us a practical way to count atoms and molecules just by weighing them.
That is the bridge. From the invisible world of atoms to the lab bench. Brilliant.
It really is. It allows us to relate mass, moles, and the number of particles directly.
Okay, so now that we can count by weighing using the mole, we can finally do quantitative calculations for chemical reactions. That's stoichiometry, right?
Precisely. Stoichiometry, stoichiometry, is the area of chemistry that deals with the quantitative relationships between reactants and products in a chemical reaction. Basically, calculating how much stuff reacts and how much stuff is produced.
And the key tool for stoichiometry is?
The balanced chemical equation. It's absolutely essential. A balanced equation doesn't just tell you what reacts and what forms. The coefficients in front of each chemical formula tell you the relative amounts in terms of molecules, or more practically in terms of moles.
Okay, give us an example, like burning methane.
Sure. The balanced equation for methane combustion is CH0 plus 2O plus 2HO.
Right.
Those coefficients, the unwritten one for CH0 and CO and the 2 for ECO, tell us that 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water.
Or scaling up using the mole.
Exactly. It also means 1 mole of CH4 reacts with 2 moles of O to produce 1 mole of CoO and 2 moles of HO.
And since we know the molar masses, we can convert those mole ratios into mass ratios.
Precisely. We know 1 mole of CH is about 16 Gs, 1 mole of O is 32 Gs, 1 mole of 2 is 44 G, and 1 mole of HO is 18 G. So the equation tells us 16 grams of methane reacts with 2 by 32 equals 64 grams of oxygen to produce 44 grams of carbon dioxide, and 2 by 18 equals 36 grams of water. The balanced equation gives us all those quantitative relationships.
That's incredibly powerful for predicting yields or figuring out how much reactant you need. Now, what happens if you don't mix the reactants in exactly the right stoichiometric ratio?
That leads to the concept of the limiting reagent, or limiting reactant.
The one that runs out first.
Exactly. In most real-world reactions, especially in industry, you don't mix reactants in the perfect mole ratios. One reactant will get completely used up before the others. That reactant is the limiting reagent because it limits the maximum amount of product that can possibly be formed. The other reactants are said to be in excess.
So identifying the limiting reagent is crucial for knowing the theoretical yield of a reaction.
Absolutely critical for process efficiency and economics.
Okay. And one last area. Many reactions happen when substances are dissolved in a liquid, usually water, in solutions. How do we talk about amounts then?
Right. We need ways to express the concentration of a solute, the dissolved substance, in a solvent, the dissolving liquid. There are several common ways.
Wait.
Mass percent is one. It's simply the mass of the solute divided by the total mass of the solution multiplied by 100.
Okay.
Mole fraction X is another. For a component, it's the moles of that component divided by the total moles of all components in the solution. Mole fractions for all components always add up to 1.
Right.
Probably the most common unit in chemistry labs is molarity. That's defined as the number of moles of solute per liter of solution. Moles per liter, molarity.
Molarity. Very common. Any drawbacks?
Well, because molarity is based on the volume of the solution, and volume can change slightly with temperature. Liquids expand when heated, contract when cooled. Molarity is temperature dependent.
Ah, interesting. Is there a concentration unit that avoids that?
Yes, molality. Molality is defined as the number of moles of solute per kilogram of solvent. Moles per kg, mol. Since mass doesn't change with temperature, molality is temperature independent, which is useful for certain physical chemistry applications like studying colligative properties.
Molarity per liter solution versus molality per kg solvent.
Got it. And if you had a concentrated solution and want to make it less concentrated?
That's dilution. There's a very handy formula for dilutions. MUO, MVA, VS, where MUO and VO are the initial molarity and volume, and MUO-V are the final molarity and volume after adding more solvent. It's based on the fact that the number of moles of solute stays the same during dilution.
Super useful in the lab, I bet. It really does all come back to quantifying things precisely, doesn't it?
It absolutely does. Chemistry at its heart is about understanding matter and its transformations quantitatively. These concepts, moles, stoichiometry, concentration, they are the tools that allow us to do that effectively. Wow. We have really covered a huge amount of ground today.
Yeah.
It's amazing to think about that journey from, ancient alchemists dreaming of gold and immortality, and Indian sages thinking about the paramonu, the atom, millennia ago, all the way to modern chemists designing life-saving drugs and incredible new materials we use every day.
It's quite a story.
And it's all built on this precise understanding of matter, how it behaves, how it changes, and how we measure it using these fundamental laws and concepts like the mole. This deep dive has hopefully given you a really powerful foundation for understanding chemistry, how it works, how we quantify it, and just how deeply it impacts, well, every single part of your world.
And maybe here's a final thought to leave you with. Considering that ancient Indian texts were discussing concepts like the paramonu thousands of years ago, and ideas that seem remarkably similar to nanotechnology showed up in traditional Ayurvedic medicine, well, what other profound insights from different historical cultures might still be out there waiting to inform our cutting-edge science today?
That's a fascinating question. And also, as we keep refining our fundamental SI units, like we talked about with the kilogram now being tied to a universal constant, what new doors might that open? What new level of precision and understanding about the universe might become possible? Something to ponder. For now, I really encourage you to just start noticing the chemistry happening all around you, in the kitchen, in nature, in technology. It truly is everywhere you look. Thanks so much for joining us for this deep dive.